exciting, not super urgent, but exciting enough. Number 1. As we talked about last week, you have Alex due today. You have Alex due Friday night at midnight. Those are this week's objectives. So the things we'll learn today and on Wednesday, those are due Friday. Your final exam is next week. It is next Wednesday. It starts at 3. If you have I'll call it an adult job. If you have somewhere that requires you to be there at 3 o'clock on Wednesday, please let me know. It will be here at 3, which means on Monday there is no class if this is your first semester at UNF. On Monday at 3, I will be giving you a different final. You can do whatever you'd like. Study, anything else. The final is 200 points. You have 110 minutes, which is an hour and 50 minutes. It'll be the whole time. It's of similar length-ish to the midterm exam that we took, I don't know, many months ago in the middle of the semester. Your PI completion is due at the start. So on Wednesday at 3 o'clock, your Alex will close. Not Wednesday in 2 days, Wednesday in whatever, 9, I don't know. I can't do math, it's the end of the semester, life is hard. At the end of the semester, when we start the final, it's over. If you have any questions about Alex or about the final, so if you are like, oh wow, I knew it was coming, but I didn't know it was next week, here are some help sessions that you might want to peruse if they work for you. So SI is tomorrow night. I have no idea what time it is, so like you should know. Tuesday is a regular session. Thursday will be an extended session. It is face-to-face on campus. I don't know what time. She said she would send out an announcement. Friday is a Q&A session for her. That one, so Tuesday and Friday are on Zoom. Thursday's face-to-face. If none of those work for you, the alternatives are to see me, that sounds mean, my office hours. I have office hours tonight from 6 to 6:45. Tuesday, which is tomorrow, from 4:30 to 5:30. Wednesday, 12 to 2. Friday, 11 to 12. I want to give you lots of options. I don't want to say have many things to do, so if no one shows up, I'll be fine. But I do want to offer a review. So, on Sunday, at a time to be I need to check the NFL schedule and see if there's any games I want to schedule my day around. It will likely be in the afternoon. It will be on YouTube Live. So, if you're like, interesting platform choice, it's true. YouTube Live will allow you to sign in. You can watch. Unlike Zoom, there is no camera interface, which I personally really prefer. Teaching to the Zoom black wall of death is terrible. At least on YouTube Live, I can pretend that it's not just my dad watching. He usually texts me and is like, "You're looking great today, Professor." It makes me so happy. You can come if you have a YouTube account. I do not care what your username is. I will call you by that. If you feel like it would be very uncomfortable and your name is, I don't know, not polite, make another account. If your name is the Dragon Master 5, I will just say, Dragon Master 5's question is blah, blah, blah. I don't care. It'll work. The other advantage of YouTube Live is it will automatically record and post. It is optional. I am going to arrive with some version of prepared questions. I will post the questions as a PDF afterwards, because I'll probably not be ready before that. It will be online. There will be office hours next week. I don't know when they are. I will update you accordingly. If you have questions, I'm happy to answer them. The YouTube Live auto records. I will post that in an announcement in case you're like, I don't want to go to that live. If you have questions, you can email me, and I'll answer them in that. I lost my influencer light, so it will have bad lighting, so we'll just all cope with that. Or I'll buy another one between now and then, but it'll be fine. Questions about any of this information? Or about the final, or about Alex, or about, yeah.
what we left off on the midterm? Or is it like something like?
It's the whole semester. So it is cumulative. You can use your midterm or any of the mini exams as studying. Keep in mind, most of the course kind of builds on itself. So like at some point you can see that we'll get thematic themes. Nothing that I've previously not tested on will be tested on. I can't think of any examples, but people always ask, like, is it going to be new? The only new material is this week's material. Everything else you have been quizzed or tested on before. I do not recycle direct questions, so please don't go memorize the keys and hope for the best. I mean, you can do that, that's fine, but you should know how to do all of those. If you have questions, I'll happily answer them. Your mini exam 6 scores are in my bag and graded. I will post those today. All of this will happen as fast as I am humanly allowed to like move. Scores will post. I will update it to drop the lowest 2. I've done enough tests in like my own Excel spreadsheet. No one's grade should go down. As far as I don't know how it would. Should be in your favor. For your Alex, 2 of the on-time submissions will drop. That's already in there. I think that's everything I have to tell you. Oh, I will update Alex scores tomorrow and on Saturday so that you can play the how many points do I have to get on the final to get whatever letter grade I want. It's a fair game. I've played it. I would sit there. I would spend more time calculating that instead of spending time on like learning things. Those are refreshing to know. I needed 3 points. You get a B. Whatever weird scores it was. Any questions? Yeah.
You said 2 Alex scores will be dropped.
Mm-hmm.
So if you've done all of them, and so it's not going to change anything, right?
Yes. That should already be in there. It's in there on mine. It like turns them orange when it drops them. I don't know what color it is. My spreadsheet goes like this, and yours goes like this, so I don't know if it grays them out or whatever it does. But it should be somewhat automatic. All of that should be in there. I don't remember if it was you. I know some of you guys have already finished your pie. In that case, nothing will change. If you've already finished it, you've turned it in advance, and so it will be 10s out of 10s for that. Any other questions?
Sorry. So whatever percentage we have on for the Alex pie right now is like what our completion grade would be on the.
Yeah, your Alex pie. So when you sign in, it's like, welcome, and then it says your name, and then it has like a pie thing in the middle, and it's either a percentage or a value. If it is a percent, that is the percent of your pie. Okay. So if it says 12, you will get 12 points. If it says 100, you will get 100 out of 100.
So if I choose select stop, I can't think of like 98, that would drop my lowest score for the Alex.
Those are 2 different pots.
Okay.
Fair question. So your Alex pie score is not droppable.
Oh, right, we'll probably get 98 and then like the Alex objective position will have to do with that drop.
But if you've done 98, you can show me, if you have your computer, show me after and we can look at it and I can give you a better. I feel like we're playing with fake numbers and I don't want to tell you like, yeah, it'll look like this and then it definitely doesn't look like that. But yeah, we can look at it. Any other questions? So let's talk about chapter 10. So in chapter 10, we're going to start to talk about gases. The first 30-ish minutes today are a lot of like information. We will do math as we proceed. If you own a textbook, we are only going to do roughly the first half-ish to 2/3 of the chapter. So what is at the end is not covered, and we're not going to worry about that. So, gases. If you say, do you have any gas? If you ask me about my lab, either way, most of the time I don't think about air. I either think about gas in the car, gas lines, like things that catch on fire, or anything else, but it never really occurs to me to think about like the air in here as being a gas. So what makes something a gas? A gas fills any container. One thing we know with balloons is as you inflate the balloon, if you put it inside a container, it will fill the container. So it will spontaneously fill the container, and it basically expands to fill it. So if you look at a scuba tank, if you use half of it, the tank doesn't compress. You still have a fully formed tank. So mixtures of gases create homogeneous mixtures. If you cast your mind back to very early in the semester, a homogeneous mixture means it's not separatable. So I think of homogeneous mixtures as things like mixed drinks. It's impossible to change their two things. You can't, if you mix different things together, you cannot separate those easily. Unlike Fruit Loops and Cheerios, you can look at those and say, these are two different things. So that would be a heterogeneous mixture. It deserves a small star because part of what happens at the end of chapter 10 is to talk about when gases do not create homogeneous mixtures. Most of the time they do. For the purposes of Gen Chem 1, they're only homogeneous. For the purposes of real life, it's not necessarily that way. You have different types of gases that have different densities, and so you can get some layering to some effect. So some gases are vapors. So when we think about vapors, or when we think about water as a gas, that's water vapor or steam. But the reality is that even when you say water vapor and steam, I still think of it as just liquid water in the air. Like, I don't think about it as being gaseous. It is gaseous. So in some of the problems, it will say water vapor or vapors. That is code for it's in a gas. And so gases, one of their other characteristics is that they're highly compressible. This is true in scuba tanks. This is true if you have a butane torch, which has usually gaseous butane in there. They pack it full of air, and then it is still a small container because otherwise you would have to carry around giant containers of air for things like hairspray or if you went scuba diving or other types of things. So these are some of the ways that we know that something is a gas. So how do we measure that something is a gas? What unit are we looking for here? We're going to use pressure. So pressure is if you wanted to think about how do you calculate pressure, it's the force divided by the area. So the pressure, if you calculate for certain things, it's often the force over how big of an area something is standing on. In Gen Chem 1, we are not really going to calculate pressure. We're going to use the pressure that is provided to us. So gases around us exert pressure on everything. It's called atmospheric pressure, and it changes. We know this. When a front comes through, a hurricane comes through, a big storm, we see changes in the atmosphere that may, for myself, I get a big headache. Can't usually tell it's going to rain. And so the pressure units, the SI is Pascal. So 1 Pascal equals 1 Newton per meter squared. This formula, I don't want to say not important. We're not going to use it a lot in this course. This is more of what is pressure. I don't say philosophically because that sounds cheesy. But what is pressure on a bigger scale? So how do we actually use the idea of pressure? How do we measure pressure? Gases inherently don't have weight. If you wave your hand around, it doesn't feel like you're moving any type of molecules. So inherently, people think about gases as being weightless. If you have enough gas, like a lot, it will weigh something. So we know they exist. We know you can remove them. You can basically pull all of the air out of a plastic container and it will crumple. So we know that it is there, but how do we measure that? So you can use the Taurocelli Barometer. So in the olden days, Taurocelli took a dish of mercury. Now, this is, as I said, the olden days, before we knew that mercury was toxic. Mercury is a liquid, it's super cool, but it is in fact quite toxic. This is a dish, like a platter full of mercury. So he has a glass tube that is sealed on one end and is at least 760 millimeters from the surface. So what he noticed is that under normal atmospheric conditions, I believe he was in France, this is how much mercury went in the tube. As he took his quite toxic dish of mercury, took it out to the sea, he took it up to the mountains, carefully of course, what he noticed is that the pressure started to change. And so what they did is they would leave these dishes around and say like, oh, the pressure is changing, it's gone up or down. So on the bottom of this slide, there are a bunch of different units for pressure. All of these will be on your equation and constant sheet. Please don't memorize any of them. In my previous course, someone asked if I would post the equation sheet for the final. It is on my list of things to do between now and when I see you on Wednesday. And it should look the exact same as it did, or it will on the final. So in this case, 760 millimeters of mercury is equal to 1 atmosphere, which is equal to 760 torr, which is equal to 101,325 pascals, or 1.01325 bar. These are all the, I mean, they're not all the same, but they're all equivalent. So different scientists or groups of scientists select different ones. So my research uses pressure to do things. We measure in millimeters of mercury. Basically, that's the readout that you get. When we think about other things, they talk about PSI or pounds per square inch. Most chemists use atmospheres. When we think about weather people, they tend to use bar or different units. All of this is to tell us they're all slightly different, but they're all equivalent. So one of your ALEKS objectives will be basically to interconvert between the units. You just need to look at this and set it up like a unit conversion you would any other time. What questions do we have thus in this moment? So that's all to tell you that there is gases and pressure. So let's think about what we can actually do with that. So in this case, in the 1600s, a lot of different things were noticed about gases. So this is to start to tell us about gas behavior. So there are 4 different parameters we're going to look at today. For gases, we can measure P, which is pressure. V equals volume. N is the moles of gas, like the molar amount within a container. And T is temperature. We tend to think about temperature in terms of Kelvin. Moles is in moles, and we'll talk about the types of different units for pressure and volume in a little bit. So these trends led to significant observations. So the first one is Boyle's law. So Boyle's noticed a couple of things. He noted in this schematic on the side that if he had 60 mils of gas, which is the purple behavior in the leftmost tube, when he compressed it, or he doubled the pressure by adding more mercury in the tube, he compressed the gas. So basically, the gas went from 60 to 30 when he doubled the pressure. So this is considered the pressure volume relationship. And what he noticed is that the volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure, otherwise known as pressure times volume is equal to a constant. Or you might have also seen this written as V equals 1 over P multiplied by a constant. So this basically states that in this case, temperature is constant. In certain conditions, when you change either the pressure or the volume, we see we see proportional changes. In Charles's law, Charles looks at volume and temperature. One thing we may know here in Florida is if you have a balloon and it gets cold, so if you take a balloon and you put it in the freezer, it will shrink as the gases contract. So when the volume of a given system at the same pressure and temperature, at higher temperatures it expands, at lower temperatures it contracts. So at high temperatures, high temp, same pressure, the volume decreases, and at low temperatures, but also at the same pressure, the volume, whoops, that should be backwards, sorry. Volume decreases, which means that the volume divided by the temperature is equal to a constant. Yep. Any questions? So within the discovery of Charles's law, Lord Kelvin determined, right, first identified absolute zero. So when we talked about temperature, in like chapter 1, a long time ago, where we talked about Fahrenheit, which is the American system, Celsius, which is the metric system, and Kelvin, which is often the scientific system. So the Kelvin system originated from the reality that as you decrease the temperature, so in this graphic on the x-axis we have decreasing temperature, on the y-axis we have volume. For a given balloon, as you decrease the temperature, it creates a linear line. That line, as you continue to extrapolate it, leads to a place called negative 273 in Celsius. This is 0 Kelvin. 0 Kelvin is the temperature at which there should be no volume. So volume should equal 0. Now, one thing we might note is that you cannot compress something into nothing. You can make it as small as possible, but it actually won't go all the way to 0. So absolute 0 will make it, everything is going to be as contracted as possible as you get close to that. But it doesn't go to nothingness because that would be creating a black hole, and that's in fact bad. So in this case, what we see is that at low Kelvin values, between 0 and 10, you can actually watch bonds move around, or you can watch electrons move. You can slow down how fast things happen at really low temperatures. But at 0 Kelvin, we do not, in fact, compress gas into 0 volume. This is where the Kelvin scale originated from. It's all based on the idea that at 0 Kelvin, you should have 0 volume. Any questions?
That to say that 0 Kelvin hasn't been achieved, or that it doesn't actually remove mass from the gas?
As far as I know, the lowest people have gotten is between like 3 and 5 Kelvin. I think it's exceptionally difficult to cool things down to that degree. Just as far as I know. I feel like they would have won a Nobel Prize. We do know that once you get to 3 and 5 Kelvin, there is a place where the volume no longer changes. So you cannot compress to nothing. Because at some point, if you put, this room is a good example. Most of you sit next to no one, right? So if you only saw the 4 feet around you, you might imagine that you're the only person in here. If I continue to be like, well, you can't sit in the back row, can't sit in any of these seats, you guys would at some point run out of empty seats. So it's the same philosophy when we think about 0 Kelvin. The air molecules have mass. It's just so small relative to the space that as you continue to compact it, the molecules run out of empty space to participate in. So as far as I know, if you go to 0 Kelvin, there will still be volume. And so in other chemistry courses, they studied the deviations from the ideal gas law, which are really due to the fact that at 0 Kelvin, there is still some level of volume around. There are a few other weird quirks that lead to non-ideal gas behavior.
So then the compression is just kind of getting rid of the empty space between the molecules, but you still actually have to keep the space for the molecules.
Yes, you can't. I can make you guys get closer and closer and closer together, which I'm not going to do. No one panic. But at some point, I could not be like, you guys must be on the same square, right? I mean, I could. That would be very uncomfortable, and I would never do that. But you guys are physical beings. That sounds like some of you are not. Sorry. But at some point, you take up space. And so there's no way for you and another physical being to be in the exact same space without some weird creepy stuff happening. Any other questions? Oh my God, this semester. I'm ready for it then. Avogadro's law. He is our friend. We met him in chapter 3, where we learned that there are 6.022 times 10 to the 23rd of anything per mole. He arrived at that information using this law that he developed. So Avogadro determined the following. At constant temperature and pressure, the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of gas. Now, it's important to note that Boyle's and Charles are the same system, but you cannot, in fact, double the number of moles, just like, I won't say willy-nilly, but in order for this to be true, it has to be two systems under identical conditions. Because, as we've learned all semester, 1 mole does not spontaneously come into 2 moles if we just give it more space. So in this case, it is 2 systems under identical conditions. And what we learned is that the volume is proportional to the number of moles, and that is also equal to a constant. We'll say note, these are 2 identical systems, which I think is an important point to make, because in a second we're going to combine all of these laws. So as we look at Boyle's, Charles, and Avogadro, what we realize is that they're all very similar equations, where pressure times volume is equal to a constant, volume over temperature, constant, volume over moles is also equal to a constant. If you were to manipulate these by solving for V, or the constant, we would eventually determine that the pressure times the volume divided by the moles times the temperature is equal to a constant, which is similar to the equation that we, I don't want to say know and love, but we know where PV equals nRT. Where R is the only value we don't know, and this is the gas law constant. So, R is a constant. When we were over here, I said that temperature was in Kelvin, N is in moles, which is also a unit. But pressure and volume, there isn't necessarily a singular defined unit. And the reason for that is actually because there are multiple different R values. So in this table, which will be not reported in this way, but it will basically be that R equals and then a bunch of values with their units on the table, no, on the equation sheet. If we look at this, liter, atmospheres, moles, Kelvin, or you can have meters cubed, Pascal, mole, Kelvin, liters for mole, Kelvin. Now, these two right here, we don't use them very often, and definitely not often in gas law equations. These two give rise to some other phenomenon. When we start to think, you may have seen them, I think in an Alex explanation in chapter 5. The gas constant will be provided. Please do not memorize that. I liked the first one because I know it by heart at this point in my career. You may choose whichever one you like depending on what units you want to use. So let's look at how we can look at these questions. So a scientist is adding chlorine gas to their reaction through a small balloon. How many grams of chlorine are contained within the 347 milliliter balloon at 36.2 degrees Kelvin and 1.134 atmosphere? So in this case, one of the difficult parts about chapter 10 is actually the reality that, one, there's a whole bunch of numbers up there with many units. I think the best plan of attack with these is to write out everything in the problem and then go forward, as opposed to just starting to plug information into a calculation and kind of cross your fingers and hope that you end up in the right place. So we know that we are going to use PV equals nRT. So the values I would write down is that the pressure equals 1.134 atmospheres. The volume is 347 mils. The temperature is 36.2 degrees Celsius. And I'm going to select an R value. You may pick any of these you like. I'm going to use this first one. The reason I'm going to pick that one is because I already have atmospheres, and milliliters to liters is a really easy conversion. You could, again, pick anything you want, as long as all of your units are the same. So I'm going to choose R of 0.08206 liters, atmospheres, mole, Kelvin. Now I need to make sure that my units are going to match. Liters, atmospheres, good to go. Milliliters to liters, there are 1,000 milliliters in 1 liter, so we get 0.347 liters. Now, Celsius, I will either give it to you in Kelvin or Celsius. I'm not giving you any temperatures in Fahrenheit. Now what Alex does, that's between Alex and Alex, I will only ask you to go from Celsius to Fahrenheit. Nope, Celsius to Kelvin. To do that, we add 273.15, and that gives us 309.35 Kelvin. So if we're going to use PV equals nRT, we're solving for the grams, which we can get to from moles. So N equals PV over RT, which gives us 1.134 atmospheres, 0.347 liters, 0.08206 liters, atmospheres, mole, Kelvin, multiplied by 309.35 Kelvin. Once we plug this into our calculator, hopefully what you get is 0.015506 moles of chlorine gas. This question asks for the value in grams. Yes? Since it's in the middle calculation, I will leave all of them, but in the final answer, which is the next step, you should pair back to your sig figs. Good question. So it asks for it in grams. To get to grams from mole, we are going to multiply by the molecular weight, which for chlorine is 70.90 grams of chlorine in 1 mole of chlorine gas, which gives you 1.09937 grams. And as you rightly pointed out, we need to remember that sig figs are a thing. And based on the question, I see that there should be 3. And that gives me 1.10 grams of chlorine gas. What questions do we have about this calculation? Yeah.
I got one from the denominator of the fraction where the liter times atoms over mole times K is.
That's liters, atmospheres, moles, Kelvin, and those are the units for this calculation.
Right. Wouldn't the mole value cancel out with the N on the other side? I'm sorry, I'm just kind of trying to mentally work myself through the math still. And I'm catching up.
Your answer should be in moles. And it flips to the top of the equation because when you divide by an equation, it flips. We are going to struggle to remember some of our algebra today. I will tell you in the points when it comes out, but that's one of them. Other questions? Why don't we give this one? We're calcium carbonate, which is CaCO3 solid. The principal component in limestone decomposes upon heating to calcium oxide and calcium dioxide. A sample of calcium carbonate is decomposed. The carbon dioxide is collected in a 250 milliliter flask. After decomposition is complete, the gas has a pressure of 1.3 atmospheres at a temperature of 31 degrees Celsius. How many moles of carbon dioxide gas were generated? So in this example, it's not fully identical, but it is very similar to this. It is purely happenstance that we solved for moles twice in a row. You will be asked to solve for anything other than R, but you would be provided, so if there are 5 values, you'll be provided 3. You can get an R value, you'll solve for the last. So in this case, we want to write out what we know. The pressure is 1.3 atmospheres. The volume is 250 mils, which is a 0.250 liters. The temperature is 31 plus 273.15, which gives me 304.15. From here, we are going to set up basically the same thing. And so using this information, we know that the pressure is 1.3 atmospheres. The volume is 0.250 liters. We have 0.08206 liters, atmospheres, mole, Kelvin, multiplied by 304. Thank you. 15. I don't know where it went. So in this case, our N is 0.013 moles of CO2. So what questions do we have about either of these two examples? Yeah.
Well, we have to memorize the R values.
No. I will provide all of them on the equation constant sheet, whatever you want to call that. And like the midterm, it will be a separate packet. And I will post it minus the periodic table that you've seen sometime between now and Wednesday. Hopefully today when I go back up to my office. But other questions? There's nothing I'm presenting this week that I'm asking you to memorize, as far as I know.
The 0.08206, can we just like always use that for like any type of problem like this? Will it always work?
As long as your units are correct, yes. But what you'll see in Alex is it might give you, so in this table, if it gives you liters and then the pressure is in torr, you have two choices. You can convert torr to atmosphere, which is what I tend to do, or you can use this other value. Those are kind of whichever one works best for you. I tend to only use one of them because it's instant recall. You can use either one, and they will get you to the same or a similar enough answer. Other questions? So how can we use the ideal gas law? So I feel like we talked a lot, so let's do another example. So tennis balls are filled with either mixed air or nitrogen gas to a pressure above atmospheric pressure. This increases their bounce. If a tennis ball has a volume of 144 cubic centimeters and contains 0.33 grams of nitrogen, what is the pressure in atmosphere inside the ball at 24 degrees Celsius? Which is a cool Florida day, just to be clear.
What is?
So in this case, here are our variables. We're looking for the pressure. In this case, our volume was presented as 144 cubic centimeters. There is a value that uses meters cubed. I'm going to convert that to liters because I remember that 1 cubic centimeter is equal to 1 milliliter, and 1,000 milliliters are 1 liter. So it is just 0.144 liters. To convert from 24 to Kelvin plus 273.15, which gives me 297.15 Kelvin. Now, in this case, it tells us we have 0.33 grams of nitrogen. We need that to go to moles. To go from grams to moles, we divide, in this case, by the molecular weight. Nitrogen, or N2, is 28.02 grams in 1 mole. And that gives you 0.01178 moles. I'm going to bring a few extra along of the sig figs here, mostly to give us the most accurate answer. You could have trimmed it back. Your answer should be identical. So pressure, if we have PV equals nRT, to solve for pressure, we divide both sides by the volume, which gives us nRT over V. So we have N, which is 0.01178 moles, 0.08206 liters, atmospheres, moles, Kelvin. The temperature is 297.15 Kelvin. Divide all that by the volume of 0.144 liters. After our sig figs, we get 2.0 atmospheres. What questions do we have about this example? Yeah.
So how did you manipulate from PV equals nRT to P equals nRT divided by V?
So if you want to isolate pressure, you need to get rid of the volume. If you divide both sides by V, the volume will move from the left to the right. Other questions? So the ideal gas law is fun. It's also quite repetitive. There's only really 4 different things. It's the same calculation over and over again. So if we, instead of thinking about one situation, if we think about our tennis balls. So if instead of thinking about PV equals nRT all the time, let's think about if we have a tennis ball under different conditions. So if we have an ideal set of conditions, we'll call them condition 1. So in condition 1, we have the following statement, that pressure 1, volume 1, equals nRT1. Now, the moles do not in fact have a subscript 1. In order for this system to work, the moles have to stay constant because we're going to look at the same system under 2 different conditions. When we talked about Avogadro's law, we said, Avogadro's law, we can't just create matter. So the number of moles is going to stay constant. So if we have a similar, but a different condition, so the same number of moles, under condition 2, we get P2, V2 equals nRT2. So we can solve for N times R. And this equals P2, V2 over T2. Now, for this to work, you have to have a tennis ball under 2 conditions. Now, a tennis ball, the volume is going to stay the same because the tennis ball can't get bigger or smaller. So you could rearrange this information under many different permutations, such as this permutation where P1 V1 over T1 equals P2 V2 T2. So everything changes. You could also have P1 V1 equals P2 V2. You could have V1 over T1 equals V2 over T2. Or you could have P1 over T1 equals P2 over T2. I will give you this one and this one. For the many different variations of two of the three variables, I will give you P1 V1 equals P2 V2 as well as the one with temperature so that you remember that one of them is on the bottom. But the reason this holds true, so the tennis ball is a good example. If you were to change the pressure and the temperature from here, you took your same, I don't know where you went for high pressure, but you took it to the bottom of the ocean, the pressure has gone up, the temperature is different. You could calculate the new pressure at a different temperature, but the volume is constant. Sometimes Alex will give you all of the information, so you can calculate through PV equals nRT and then calculate other information, but not always. So this allows us to compare and determine information about alternate conditions. So let's look at some examples. So the pressure in an aerosol can, hairspray, bug spray, whatever, is 1.5 atmospheres at 25 degrees Celsius. When the can is heated to 450 degrees Celsius, what is the pressure inside the can? So in this example, just like all of the other calculations today, what we're going to start with is writing down what we know. Kind of like dilutions, the harder part of this is the identification of what information goes together. So in this case, we have pressure 1, and that's 1.5 atmospheres. T1 is 25 degrees Celsius. T2 is what we do not know, and T2 is equal to 450 degrees Celsius. So by looking at these equations, we can use P1 T1 equals P2 T2. So from here, I'm going to go ahead and convert my temperatures into Kelvin. So plus 273, this is going to become 298.15 Kelvin, and this becomes 723.15 Kelvin. Now, we need to solve for P2. So in order to isolate that, we're going to multiply both sides by T2. So pressure 2 is equal to pressure 1, temperature 2 divided by temperature 1. So now I'm going to go ahead and start plugging in our values. Where we have 1.5 atmospheres multiplied by temperature 2, 723.15 Kelvin, divided by 298.15 Kelvin. That equals 3.6 atmospheres. So when we start thinking about this calculation, some of you might be thinking, when we used to do M1 V1 equals M2 V2, as long as the units were the same, we could just kind of, skip over the converting part. So if you plug that into your calculator, in this case you will get 27, which is in fact not 3.6. And the reason we can't do that, because I think it's important to actually explain why, because just because is like a sad answer. So if instead of this, you had actually calculated 1.5 atmospheres. And then you put in 25 plus divided by the 450 plus 273.15. So if you you'd said, hey, they're Celsius, it should all work out. The reason it doesn't is because we can't cancel things that are not on both sides. And it turns out we can only cancel things that are multiplied. So if all three of these values were added plus 273, we might be able to do something different. But because just these two are, you cannot cancel algebraically the unit conversions from Celsius to Kelvin. I say all of this because it feels like the units are the same, we can skip out. So you can't in this case because of algebraic mathematics rules. What questions do we have about this calculation or any of the other parts of that?
How did you derive the formula that you used, as in the T1 over T1 equals P2 over P2?
In this case, because the aerosol can doesn't change volume, I excluded the volume from this one. Other questions? Fantastic. Why don't you give this second one a go? An inflated balloon has a volume of 6 liters at sea level, where it's 1 atmosphere, and is allowed to ascend, that means it goes up, until the pressure is 0.45 atmospheres. During the ascent, the temperature of the gas falls from 22 degrees Celsius to negative 21 degrees Celsius. Calculate the volume of the balloon at its final altitude.
You're missing one of the variables. Exactly right.
look at this together. So I personally, in these, it becomes increasingly more important to actually write down all of the different values so that you can actually see where things are going. So in this case, you can pick whether the first condition is either one. You just need to be consistent. So in this case, V1 is 6.0 liters. P1 is 1 atmosphere. T1 is 22 plus 273.15, which gives you 295.15. We are looking for V2. Pressure 2 is 0.45 atmospheres, and T2 is negative 21 plus 273.15, which gives you 252.15. Now it becomes a little bit more complicated. So first, I'm going to write the equation, then we'll figure out how to solve for what we're looking for. So P1 V1 over T1 equals P2 V2 over T2. We would like to solve for V2. In order to get the equation on the other side, you will multiply both sides by T2 and divide both sides by P2, which should give you V2 is P1 V1 over T1 multiplied by T2 over P2. The way you can make sure this is like actually doing what you want, the units should cancel out. So if you're like, oh my goodness, math, no, I don't want to make, if you bring all your units along and you set it up this way, the alternative way would be to leave it like this, run the math calculation, and then divide by whatever value you get here on both sides. From here, we can start plugging this in, where we have 1 atmosphere, 6.0 liters, divided by 295.15 Kelvin, multiplied by 252.15 Kelvin over 0.45 atmospheres. And after our sig figs are done, I get 11 liters. That doesn't look like anything. How do I try to make it darker? What questions do we have about this calculation? Or other calculations that we've looked at today? We do not have enough time for the next topic. So, with that, we are done. I do have your mini exam 6s. If you would, I definitely want you to take it home.